Geometry, we have rules that we accept so that we can do geometry. Those rules are called postulates, sometimes called axioms. So these postulates or axioms, these are things that we just accept as being true. We just say, all right, we're gonna look at this rule and say, yep, that's true, and then we're gonna accept that that's true so that we can do geometry. And we just do geometry based on those rules that we set up. We don't have to set up the rules this way. This is just how we've set up the rules to do geometry in this particular way. But there are other ways you could set up postulates, accept different things or not accept other things, and you can get different types of geometry from that. But in this one, we're going to look at some postulates that we're just going to accept for this class so that we can do the geometry that we're going to learn in this class. Okay, once you have postulates, you can then prove things based on those postulates, and those things that are proven we call theorems. So a theorem is something that is proven based on postulates. So it's something you know is true based on those postulates. Postulates and theorems are often written in conditional forms. However, unlike definitions in the last lesson, the converse of a postulate is not necessarily going to be true. Sometimes it will be, but you can't just assume it's going to be true like you can with a definition. Let's look at some postulates. So again, these are things that we're just going to accept as being true. We've already looked at a few of these. So postulate 1, the ruler postulate, this was just saying that we can basically turn any line into a number line, put numbers on it, and kind of mark off numbers. Postulate 2 is the segment addition postulate, which basically said if you have a segment that's this long, and then you add to it a segment that's this long, you end up with a segment that is that long. Protractor postulate, angle addition postulate, similar things, just allowing you to measure angles with a protractor, allowing you to say that if you take this angle and add to it this angle, you get this entire angle. Now we're going to look at some more postulates. Postulate 5. Through any 2 points, there is exactly one line, which basically means that take any 2 points on a plane and you can draw a line between them. There's only one line that you can draw between them, or rather one straight line. So if we have 2 points like this, of course I can draw a curved line that goes through those two, but there's only one straight line that will go through those 2 points. Postulate 6. A line contains at least 2 points. Well, that makes sense too. You know, if you just have 1 point here, well, of course I can draw a line through that, but I could draw any kind of line. There's infinitely many lines I can draw through that. So 1 point is not good enough to define a line. We need at least 2 of them. You know, so if we have another point, say right there, then we can say, okay, this line is going between these 2 points here. That's where the line is defined. Postulate 7. If 2 lines intersect, then their intersection is exactly 1 point. So that means that any 2 lines, they're not going to intersect in 2 different places. Again, I could take that line and then like a curved line, and then they intersect in 2 places. But when we talk about lines, we're talking about straight lines. So if you have 2 straight lines, they're going to intersect somewhere, unless they're parallel, of course. But they only intersect in 1 place if they intersect. Postulate 8. Through any 3 non-collinear points, so that's, again, points that are not all on the same line. So through any 3 non-collinear points, there exists exactly 1 plane. We talked about this actually at the beginning of the year. So if you remember me talking about trying to balance a board or a book or something, if you try to balance it on 1 finger, you can't do that. It's impossible to balance something on 1 finger because it's going to wiggle all over the place. If you try to use 2 fingers, well, you can still rock it back and forth, but it's a little bit more stable. In order to make it completely stable where it's not going to move at all, you've got to use 3 fingers, 3 points to make that a stable, flat, 2-dimensional surface. That's essentially what this is saying here. So through any 3 non-collinear points, there exists exactly 1 plane, meaning that we can draw a flat, 2-dimensional surface through any 3 points that are not all on the same line. Postulate 9. A plane contains at least 3 non-collinear points. That's pretty much exactly what we were saying in postulate 8. It's a fairly similar statement there. Postulate 10. If 2 points lie in a plane, then the line containing them also lies in the plane. So if you imagine this screen being a plane, a two-dimensional flat plane, if we have any 2 points on this screen, and then we draw a line between those 2 points, that line will also be on the screen. So it's not going to be the case that if we draw a line between those 2 points, it's going to somehow magically not be on the screen. It's got to be there. It's got to be on that screen. Postulate 11. If 2 planes intersect, their intersection is a line. So just think about 2 walls. If you have 2 walls coming together, the 2 walls intersect on a straight line. Or you can look at the ceiling in a wall or the floor in a wall. Any flat two-dimensional surfaces that intersect, they intersect on a straight line. All right. Example 1. So what this says is if we have 2 straight lines, then, and it may be kind of hard to see here, but there is a dot right there. It's indicating that those 2 lines intersect on a point. So which of these postulates says that if 2 lines intersect, their intersection is a point? Well, that is postulate 7. Part B. So we've got 2 planes here. So think of this like, maybe a wall and a floor, except the wall and floor are extending beyond the other one. But this is saying if we have 2 planes that intersect, the intersection is a straight line. Well, that is postulate 11. Example 2. Use the diagram to write examples of postulates 9 and 10. Okay, so postulate 9 says that a plane contains at least 3 non-collinear points. Okay, so the 3 non-collinear points then that plane, let's see, the planes contain, well, we could look at plane P. So say plane P has point B on it, has point A on it, and has point C on it. So we could say then that the plane P, it contains the 3 non-collinear points A, B, and C. Postulate 10 says, if 2 points lie in a plane, then the line containing them lies in the plane as well. So let's look at 2 points on a line. Well, there's B is on this line and A is on this line here. Those 2 points are, let's see, I should be saying the points are on the plane. And if we draw that line between them, well, that line is also on the plane. So we could say point A and point B lie in plane P. So that means that line AB also lies on plane P. Example 3. Sketch a diagram showing line TV and segment PQ intersecting at point W so that TW, segment TW, is congruent to segment WV. Again, this symbol right here means congruent. It's just the geometry version of equals. That means that those 2 segments are the same length. So what we would want to do is draw some line TV. So that's a line that has point T and point V on it. And then what we want to do is draw the intersection of that and a segment PQ so that the point W, which I'll just draw on here right now, the point W is the midpoint here. So that's what this is saying here. So segment TW is congruent to segment WV. That means if this is W, we want TW, that segment there, to be the same as WV, that segment there. So we want those 2 to be the same. And then we want a segment going through here. The segment is the intersection, and that's P and Q. So again, going back to the instructions here, it says, sketch a diagram showing line TV, that's this line right here, intersecting with segment PQ, that's this segment right here, at point W, which is right here. And we want to do that so that segment TW, which is this segment here, is the same length as this segment here, WV. So there it is. All right, perpendicular figures. So a line can be perpendicular to a plane. Again, we can't really represent three-dimensional objects super well in 2 dimensions, so this picture right here is a little weird looking just because we're trying to take a 3-dimensional object and smash it into 2 dimensions, and so it just looks kind of weird. But we'll do the best we can. So, if what you want to imagine here is that this plane here, say that this is, I don't know, maybe a desk or something, and then you've got some line sticking straight up and down, sticking straight up towards the ceiling, pointing towards the ceiling, and pointing towards the floor, so that it's perpendicular to that plane. So that any angle you were to measure going up from the plane up to that line, that would be a 90-degree angle. So a line is perpendicular to a plane if and only if that line intersects the plane at a point and is perpendicular to every line that intersects that point. So that's what this is here. It's showing you that it's perpendicular to this line, and it's also showing you here that it's perpendicular to this line here. And any line, if we wanted to say draw a line going like that, it would also be perpendicular to that line. It would be perpendicular to every line in that plane. All right, let's end with example 4. Which of the following statements cannot be assumed from the diagram below? Okay, so imagine this as being 2 sheets of paper, or maybe again a wall and a floor that are intersecting right here along this line. Okay, so A, B, and F are collinear. So again, collinear means that these points are all on the same line. If we look at A, B, and F, they all lie on this line right here. So yes, that is absolutely true. Those points are all on the same line on the picture, so that means that yes, we can assume that those are collinear. All right, E, B, and D are collinear. So that's E is right here, B is right here, D is right here. Well, they kind of look like they're all in a line, but there's no line drawn that's indicating that they are collinear. There's nothing in the picture, nothing in the instructions that indicate that they really are collinear. So even though they look like they're collinear, we cannot assume that based on the picture. We can only assume that if there's some indication that they really truly are collinear. All right, let's see, segment AB, that's this segment right here. Segment AB is perpendicular. Again, that upside down T means perpendicular. So segment AB is perpendicular to plane S. S is the red plane. Well, maybe a little hard to see here, but there is a perpendicular marking there. So yes, we can assume that because it's marked perpendicular. All right, then it says segment CD is perpendicular to plane T. So segment CD is this segment right here. Well, if we look at that, there's no perpendicular marking. There's nothing on there that would indicate that that is actually perpendicular to plane T. So no, we cannot assume that this is perpendicular. There's not enough information. It could be perpendicular, but there's no markings, there's nothing in the instructions, there's nothing that tells us that they really truly are perpendicular. And the last one, line AF intersects line BC at point B. So line AF is this one here. And it's the line BC. Let's see, BC, that's this one here. It says they intersect at point B. Absolutely, right there. You can see on the picture that those 2 lines intersect at point B. So yes, we can assume that based on the picture.